Okay, we're going to continue on here, chapter 16. So we finished last time 15. Our exam is Thursday. And so 16 here, we're going to kind of mix it up with some new stuff a little bit, some maybe different things about some other topics. And we will still talk about, as you can see there, equilibrium as well, because we can't go too far without talking about that. So we're going to talk about thermodynamics in this chapter. And thermodynamics is sort of really the study of spontaneity in a lot of cases. It deals with the idea of whether or not a reaction will take place and will it be spontaneous. And you dealt with thermodynamics, sort of the first law of thermodynamics, which had to do with the energy and like Chem 50, all that kind of enthalpy and change in enthalpy. So we'll see that again. A reminder that as we know, delta H is our change in enthalpy. And when we talk about a delta H that has a negative value, that is a exothermic type process. When we have a delta H that's a positive value, that's an endothermic process. And as you learned, and as you probably know, when we talk about sort of the flow of energy, if somebody sort of loses a certain amount of energy, somebody else will gain the exact same amount of energy. In terms of sort of the values, they're really the same. The only difference really is a lot of times the sign, depending on sort of which way the energy is sort of flowing. Again, if it's an exothermic type process, your energy value should be a negative sort of sign. If it's an endothermic process where they're sort of absorbing energy, should be a positive sort of value. So when we talk about spontaneous processes, like I said before, sometimes people have a sort of wrong idea about sort of what the idea of spontaneity means. And if we sort of discover that a reaction is spontaneous, it doesn't necessarily mean that it will occur really fast. So sometimes people think spontaneous, they snap their fingers and the reaction will sort of occur really, really fast. In this sort of context, what spontaneous means is under those particular conditions, we would expect this reaction to actually take place. And that reaction could take place really fast, it could take place really slow. But under those conditions, we would expect the actual reaction to actually occur. Again, could be really fast, could be really slow. When we talk about how fast or slow a reaction takes place, is what we talked about at the very beginning of the semester, which is the kinetics of a reaction. So kinetics sort of deals with how fast or slow. When we look at sort of the thermodynamic sort of properties, we're dealing with whether or not under those conditions a reaction can even sort of take place. And again, without really the idea of how fast or slow when we talk about something being spontaneous. So that's what you should have in your head, is the idea if a reaction is spontaneous. It doesn't really necessarily mean how fast or slow. It just means under those conditions, it should definitely take place. Now, there's a lot of physical and chemical processes that we know that are spontaneous. And here are some examples of that. Water runs downhill on a waterfall. If we take a lump of sugar, it will dissolve in coffee. Water freezes 0 degrees Celsius and melts also at 0 degrees Celsius. The flow of energy always goes from the hotter object to the cooler object. Hotter object cools down, cooler object warms up. They maybe meet somewhere in the middle. Iron exposed to oxygen and water, and a little bit of moisture is pretty much all you need for rust to form. If you're skiing, going downhill is pretty spontaneous. You just need to go over the hill there. This is a non-spontaneous process. You can't find yourself at the bottom of the hill and just magically gonna go up. You have to put some type of work or energy into doing that. I'm assuming that's not what you want to see when you're going down the hill, somebody coming up the hill if you're skiing. But again, these are spontaneous processes. A couple of other examples here. If we have a gas sort of in a chamber here, separated here by a valve, and if we open the valve spontaneously, these gas molecules will find their way kind of to the other side and fill it up. A non-spontaneous process would be if we had gas molecules on both sides, probably non-spontaneously, they will not just all decide to go that way. That's probably not going to happen unless you sort of encourage them to kind of go that way. So that's definitely a non-spontaneous state process that's occurring. So when we talk about enthalpy, which is again that change in energy or the heat of a reaction, does it necessarily mean that a reaction will proceed spontaneously. So does enthalpy play a big role in terms of spontaneous reactions? So here again are some spontaneous reactions, and if we look at them, we do have some that are exothermic, like our combustion reaction here, the formation of water. These guys are exothermic type of processes. And we also have the melting of ice and the dissolving of ammonium nitrate. These are endothermic processes, and these all happen spontaneously. As we know, if we take an ice cube out and just put it outside in the open air, it's going to start to melt as it picks up all the heat and energy from the surroundings, and it's going to happen spontaneously. It will just happen. You can't prevent it. And these are all spontaneous processes. So what we see here, thank you, is that we have both exothermic and endothermic reactions that are spontaneous. So we can't just strictly use delta H as sort of a factor to try to determine whether or not a reaction will be spontaneous, because as we could clearly see here, we have both endothermic, exothermic, and they're both all of them are spontaneous here. So that really can't be the sort of overwhelming factor that we look at when trying to determine spontaneity. Although when you do have an exothermic reaction, it does sort of favor a spontaneous reaction occurring, but it doesn't necessarily guarantee it. And there's other factors that can play into whether or not you will perhaps get an exothermic, a spontaneous reaction or not. So another sort of factor that we look at in terms of thermodynamics that help us sort of decide or make that decision of will this be a spontaneous reaction is sometimes we look at entropy. That should not be confused with enthalpy. So entropy is delta S, which is the change in entropy. And the entropy is actually the measure of randomness or disorder there are in a system. And entropy is a little bit different than a lot of sort of thermodynamic sort of values that we look at in the sense of sort of how its sort of sign works in a sense. So a lot of times we think about, for example, with delta H, negative exothermic things happening, things sort of increasing. With entropy, actually, as the amount of order increases or the amount of disorder decreases, the amount of entropy or the change in entropy will actually go down and become more negative. So a negative sort of delta S implies that you are actually creating a lot more order or less disorder. So sometimes people talk about entropy in terms of order or disorder. So you kind of think about it either way. But if you're creating a situation where you have a lot more order, we will actually see a decrease in the entropy of that system. And it actually will be reflected in terms of like a numerical value as a negative number. So typically we will have a delta S as negative as we start to increase the amount of disorder order that's happening. Now, the opposite is true. If we increase the amount of disorder, so we create a lot more chaos, if you will, than where we started from, what we'll actually see is the delta S will actually start to increase. And in that situation, the delta S will actually be a positive sort of value. So when you see a positive delta S, that means wherever you started to wherever you ended, created a lot more disorder that's happening in that system. We can calculate the change in entropy by how we calculate a lot of things by basically taking our final state entropy minus our initial states of entropy. And again, if the change results in an increase in randomness, we will get a positive value for our delta S. Now, probably the easiest way to sort of visualize sort of that happening is to look at when we have a phase change. So as we go from, say, solid to liquid to gas, obviously in the solid state, things are very close to each other, pretty ordered, right? Not a lot of movement, not a lot of things happening. When we get to the liquid state, they're still fairly close to each other, but a little bit more movement happening, a little bit more disorder happening. And obviously, when we get to the gas state, nobody's near each other. We got things flying around all over the place, causing a lot of disorder. So when we're in the solid state, that has a lot less entropy because, again, it's very ordered usually. And as you go to the liquid state to the gas state, we're starting to see an increase in the amount of entropy. So as we would be going sort of in this direction, we would see the entropy start to change and probably become more positive as we go to the right there. So when we look at this sort of change here, which is our ice melting to our liquid water, which as we saw before, obviously is a spontaneous process. It's also a endothermic process. This would be going from a more ordered situation in the solid state to more disorder in the liquid state. And we would expect the delta S here to actually be more positive in this case, because we are increasing the amount of disorder that's happening here. Any questions on that there? Now, disorder is related to probability. And when we talk about probability, a probable event is one where there are many ways in which it could actually take place. An improbable event is one where really it can only happen in a few ways. So if we wanted to get out of this room, for example, and let's say there were 3 doors, it's very probable that, that we should have a problem exiting, this room. If all this room had no doors, but just like a little window on the top, it's probably improbable that we all get out to the top there, out of the window and stuff like that. So when there's lots of ways that you could do something, it's probably going to happen. And improbable is, there's only a few ways to do things. So when we talk about an ordered state, that has a low probability of occurring and a small entropy. The only way to get everything really nice and ordered, right, is there's a few ways to put everything in line correctly and get it to come together correctly. Disorder state is a very high probability of happening. So, there's a more chance of screwing something up a lot of times than doing it correct. And so the probability is very high in that, and the entropy is very large in terms of that. Now, we can relate to entropy to what is referred to as microstates, and microstates is abbreviated here with a W. This is sometimes referred to as the Boltzmann equation. That's our entropy. That is the Boltzmann constant, which is on the bottom there of the slide, and that is our number of microstates here. Our ways of sort of doing something, if you will. Now, when we look at say, this example that they have set up here, we have 4 couple of sides, basically. And if we wanted to put all 4 circles, for example, on one side versus the other, there's really only one way of doing that. You could either put it on the left, which is kind of the same thing as putting it on the right, basically. Now, if we wanted to arrange it where we have 3 circles in one box and 1 circle in the other box, there are 4 different sort of combinations that you could do to get that. And if we had 6 different combinations, if we wanted to go with like 2 circles in each box, right? It is probably more probable to end up with the 2 circles in each box, right, than trying to get all 4 on the side, one side. You can think of it like a carnival game where you're tossing the balls right into the holes. Probably very hard to get all 4 of them onto the same side there. Probably more probable that you can at least get 2 out of the 4 on each side there, if you were trying to do that. So if we look at the Boltzmann equation here in terms of the entropy, S is equal to K natural log of W. For our situation, if we wanted to just get it all on one side, that would give us S is equal to K natural log of 1. Natural log of 1 is 0, which means we have a very low entropy sort of value in this particular case. If we put in there, for example, our 6, that gives us something like 1.8. So we have a much times K, we have a much higher sort of entropy value there in that situation, and it's more probable that that's going to occur. So That's why it goes back to sort of what I was saying before. There's a lot of ways that you can screw something up, which is a very high probable event, which is why people say, the entropy of the world is always increasing, a lot of disorder sort of happening, a lot of ways to screw up things. And there's only a few ways to do things sort of correctly and right. And that has a very small sort of entropy sort of value associated with it. Any questions on that there? So here are some examples that lead to an increase in the entropy of the system. When we go from solid to liquid, as we talked about, obviously, as we go from solid, a much ordered situation to a more disordered situation. So again, increasing the disorder. As we go from liquid to gas, we now have gas molecules kind of flying around, and that's definitely increasing our disorder as well. Actually, the process of making a solution actually increases the disorder for actually both parts of the solution. Remember, a solution is made up of a solute, which is typically the thing you dissolve, in the larger part, which is the solvent. So for example, if this solvent molecules here were water, before you dissolve something in it, it's a very organized, ordered way with all the water molecules basically bonded together. Also, same idea here to some type of ionic solid. That's a very, very ordered sort of arrangement of those ions together. In the case of getting it to dissolve, you pretty much have to disrupt all that. You have to disrupt the ordered ionic compound. You also have to disrupt the water and water bonds to get everything to dissolve and make new bonds. So it causes a lot more disorder sort of happening here for actually both parts of the solution, the solute and the solvent, both see an increase in the entropy that's happening to them. The other thing that we oftentimes can see that will cause a sort of an increase in entropy of something is if we raise temperature. Like if you light a fire underneath somebody, they move faster, right? So there's a lot more disorder happening. They have a lot more energy. Things are moving around a lot faster, probably because of that added energy. So that usually would increase the disorder. So all these sort of processes here, we would expect to have a delta S value of positive to indicate that we are increasing the amount of disorder that's happening. So let's take a moment for each of these here and decide, is the entropy of this system sort of increasing, decreasing? Would it be positive or negative, or delta S for these guys? Take a look at this. Condensing water vapor. So condensation means we are going from gas back to liquid. So that's going from a state where we have things flying around with a lot of disorder to a state where things are a little bit more ordered. So that should be a decrease in the disorder, or if you want to think about it, an increase in the order, whichever way you want to think about it. You might want to pick one way or the other, think about disorder or order in terms of which way you're thinking about it. And that should result in a delta S that is going to be negative in this case, as we're increasing the order in this case, should be less than 0. Our entropy should be decreasing. Any questions on that one? Forming a sucrose crystal from a supersaturated solution. A crystal is a pretty ordered solid sort of arrangement. So again, here we're increasing the order, decreasing the disorder. That again should give us a delta S here. That should be negative as our entropy is decreasing for our system. If we heat hydrogen gas from 60 to 80, we're increasing the temperature. That's going to cause our gas molecules to fly around a lot faster, right? And thus, we should then see an increase in the amount of disorder, which means my delta H should become more, or delta S should become more positive in this case. Any questions on that one? And lastly, sublimation here of dry ice. Sublimation is where we go from solid directly to gas, skipping the liquid cleanup. So definitely started at a more ordered situation here to a more disordered situation. So we got an increase in disorder. So our delta S here, in this case, it should be more positive. Questions on any of those there? So let's talk a little bit more about entropy and what is happening, and a little bit of some important differences between, say, entropy and enthalpy. Entropy is a state function. So if you remember, state functions only really matter in terms of state functions is really two parts, is sort of where you start and where you end. And as we can see here in this picture, in terms of potential energy, these guys are at the same potential energy. They started at the same spot. They ended at the same spot. The guy in the blue took the more direct route up the hill. The red guy took the more scenic route up the hill. But in terms of their final position and their initial position is really the only thing that matters. And that's why when we calculate a lot of things, including the change in enthalpy and the change in entropy, a lot of times we look at our products minus our reactants, because when we think about a reaction, where we start our reactants, right? That's like our starting, and where we end is our products, right? That's our ending. So that's why a lot of times we take our products minus our reactants. It gives us sort of where we ended versus where we started. And that, again, is really the only two parts that are really important in terms of state functions. Now, when we talk about delta H and delta S, a really important sort of distinction between them happens with our units here, and that's because there will be some formulas later on in this chapter where we will use delta H and delta S together in the actual same formula. And you do have to be careful of units. And unit-wise, delta H is typically given to you in kilojoules, while delta S is typically given to you in joules. So you do want to make sure that you watch out for that, because if you use them together and you don't convert them, you're going to be off by that factor of 1,000 in your answer and stuff like that. So that's a very common sort of issue that happens in this sort of thermodynamic chapter when we're dealing with H and S here and our different units. Now, you can look up, just like you can for a delta H value in your book, and there's a thermodynamic table for it. And as you can see here, this is, I believe, the one from your book. It's probably in the back, and you can also find, like I said, usually delta H, delta S, and delta G all together in a table. And when we look at these, as you can see, it is in joules per mole per Kelvin. They also are all going to be usually positive values here, which is a little bit different than delta H's. Also different than delta H's is with delta H's, if you went to this table or a table for the change in enthalpy for things in their natural state that are uncombined, like, iron by itself, hydrogen gas, oxygen gas, they typically have values of 0. But for entropy, you will actually find, as you can see here, you will actually find values for things like H2 that's in their standard state and stuff like that. So that's a little bit different than what you see with delta H, where things like O2, H2, these guys are zeros typically for delta H's. Um, so one way that we could calculate or use entropy to help us decide whether or not a reaction is spontaneous or not is by calculating a certain type of entropy. As I mentioned before, the first law of thermodynamics deals with really the conservation of energy. We don't create nor destroy energy, but it can be transformed sort of from one place to the next. And that's sort of the delta H that you dealt with there in Chem 50. And the second law of thermodynamics, what we're going to look at right now, which is the entropy of the universe increases in a spontaneous process and remains unchanged in a equilibrium process. So in order to sort of use the entropy to figure out whether or not a reaction will be spontaneous, is we do need to calculate the delta S of the universe. And that is composed of two things: the delta S of the system, and usually the system is also the reaction that you're dealing with, and the delta S of the surroundings. So always in sort of these type of processes, we think about the system, and then the surroundings is everything else outside of that. A lot of times what we deal with in, say, the lab, our system is like our beaker, whatever we're doing the reaction in, and then obviously the system surroundings is everything outside of that. So if you calculate the delta S of the universe and you do get a positive value, then it means that that reaction will be spontaneous. Opposite of that, obviously, is if you calculate the delta S of the universe and you get a negative value, then that reaction will be non-spontaneous. If you have an equilibrium process, then the delta S of the universe will equal to 0. So what does that mean? It means, right, in an equilibrium process, the rate of the forward direction will equal the rate of the reverse direction, right, heading in that direction. So they will equal each other, which, as we talked about with our extensive talk of equilibrium, essentially means that when something reaches equilibrium, everybody pretty much locks themselves into place, right, in terms of their concentrations, their pressures. Nothing's really going to change. They basically get locked into place. And because of that, there's no change. There's no like forward direction, reverse direction happening in a sense. There's no overall change that's happening because everything basically just stays the same. There is no overall shift one way or the other. In a spontaneous process, we're going to have some type of thing shifting for a little bit until it reaches, for example, an equilibrium condition. So that's why when we're dealing with something that's at equilibrium, we really will not get any big change happening because it's going back and forth at the same rate. So let's talk about how we calculate the different delta S's. So the first one we're going to look at is how to calculate the delta S of the system or the reaction. And that's pretty simple. We're going to take all of our products and subtract it from the delta S of all of our reactants. So basically our delta S of our system will be our delta S of our products minus the delta S of our reactants. We do have to take into account the coefficients when you go to the table. So essentially you would go to that thermodynamic table that you can find in the back of your book. You will find the delta S values for each of those. Like always, you do want to be careful when you do go into that table that you find the substance that you're looking for, and you also find it in the correct state, so that you make sure you do get the right state that's happening there. So you do have to multiply any coefficient by the value you find in that table. You can add up all the delta S's for the products and then subtract them from all the delta S's of the reactants. And at that point, that will give you the delta S of your reaction, which is basically your system in this case. So why don't we try one here? Here's some delta S values here that you would find in the table. And I think I'm missing one. Maybe have the third one there, which is maybe on your handout. CO2 is... I think it's on your notes if you have the notes, I think. It is 213.6. All right, so take a moment there, calculate the delta S of this reaction. Okay, so let's take a look at this here. And again, we're going to do our delta S here of our reaction. And by the way, when we do see this little sort of not symbol there, that usually implies under standard conditions. And remember that sort of under standard conditions, what is meant is if you're dealing with any type of concentrations, everybody is 1 molar. If you're dealing with any type of pressures, everybody is 1 atmosphere. And the temperature is typically 25 degrees Celsius. Typically, that is the values that you get out of like tables, like we just saw there previously, and in the back of the book is sort of those are the conditions of like the table values that you find. So these would be the values that you would have to go to the table to find if they were not provided for you. And again, we're going to take our products minus our reactants here. So looking on our product side there, we have 2 times the value of CO2, which is 213.6. That takes care of all of our products. We're then going to subtract all of our reactants. We also have to multiply by 2 for our CO value, which is 197.9. We're then going to add it to our O2 value, which is 205. joules Kelvin mole. And that will take care of all of our reactants, basically. That is going to get us here 2 times 213.6 minus 2 times 197.9 plus a 205. Looks like a negative 173.6 joules. It's really joules per Kelvin. I'm just going to go with joules. This two, by the way, are moles, so that's really where moles get away, is technically speaking, is sort of where those guys would cancel. But I'm just going to roll with joules here. That means in this particular case, this reaction, can I tell if it's spontaneous or not? I really cannot. So we just calculated the delta S of the system, not the universe. So what it does tell us, though, is in this reaction, is the amount of disorder, entropy, is it increasing or decreasing in this situation? The amount of entropy is actually decreasing, right? Because it's negative. So in this reaction, we're actually going from a more disordered state to a more ordered state in this case, as the delta S shows here is negative. By the way, we could actually have predicted that by just looking at the reaction, because if we just look at the equation on the left-hand side, that is like 3 gas molecules happening there. On the right-hand side, that is 2 gas molecules. So instead of having 3 gas molecules flying around your face, you only got 2 gas molecules. So that increases the amount of order. And we can actually predict, for example, in this situation, that our delta S value for the system should actually be negative because of that. So if you have some equations where you have gas molecules either being made or reduced, you could actually make a prediction as to what the sign of the delta S for that reaction should be. That's a good way to check yourself. So here, if we got a positive value, it shouldn't make sense because we're actually decreasing the number of gas molecules that are flying around, which should increase the order and should cause our delta S value here to be more negative. Any questions on that there? So as I mentioned before, that's one way you could kind of check yourself. If a reaction does produce more gas molecules than it consumes, then we would actually be creating a more disorder happening. So if we started with less gas molecules, ended up with a lot more gas molecules flying around, that's going to cause a lot more disorder happening, and we would expect the delta S to be more positive. As we just saw in that example, the amount of gas molecules decreased. So we would expect also our entropy to decrease. Now, if there's really no net change in terms of gas molecules on either side, which could happen, then it could be either a positive or negative value for the change in entropy, but it would be probably a smaller type value, but it could be either way. Now, a lot of things that you'll see in this chapter and a lot of things with thermodynamics, a lot of times they will ask you questions. They really won't give you numbers or a calculation, and they'll just kind of ask you like, hey, this is like positive, this is negative, do you think this will be a spontaneous reaction or not a spontaneous reaction? So sometimes you're not really given numbers sometimes in problems, but you can make sort of predictions based on some knowledge. So for example, here, if we look at this one, would we expect the sign of the change in entropy to be positive or negative in this case? Which one should it be? So let's take a look. So on the left-hand side, we have one gas molecule, right? That's the only gas molecule. On the right-hand side, we actually have no gas molecules. So we're definitely increasing the order, right, in this case. We have less gas molecules flying around. And as was said there, that means that our delta S here should be a negative value. Any questions on that there? So now that we know how to calculate the delta S of the system, let's talk about how we calculate the delta S of the surroundings. And again, both of these things are important because that will allow you to calculate the delta S of the universe, and you can make sort of an assumption of what is going on in terms of spontaneity. So if we have an exothermic type process like we do over here on the left, that means that energy from our system should be released into our surroundings. So under normal conditions, we would expect that the entropy of the surroundings should start to increase and should become more positive as we see an increase of the energy to the surroundings, which means everybody in the surroundings is going to pick up that energy. They're going to start flying around, moving around a lot faster, going to cause a lot more disorder to occur. So because of this added heat coming into the surroundings, we should expect an increase in the disorder of the surroundings. And thus, we should expect for our surroundings, the delta S to be a positive number for the surroundings. Now, opposite is true. If we have an endothermic reaction, all that heat and energy is going to leave the surroundings. The result of that is the surroundings is going to lose that energy, so things are going to kind of slow down, not be moving around as fast, and that's going to actually increase the order for the surroundings. And because of that, we would actually see the delta S of the surroundings become more negative. And again, because we're going to increase the order here. So there is a relationship between the delta S of the surroundings is proportional to negative the delta H of the reaction. So the delta S of the surroundings is proportional, which is what that symbol is supposed to be there, proportional symbol, to the minus delta H of the system or the reaction. So what does that mean? If we think about sort of our values, if we have a exothermic process, our delta H should be negative, and that means that the delta S of the surroundings, which is negative of the delta H, gives me a negative times a negative gives me a positive value for my delta S of the surroundings. If I have a endothermic process, my delta H would be positive. And since my delta S of the surroundings is basically equal to minus delta H, that will give me a minus and a positive, which gives me a negative value when I kind of multiply them together. So that is what is sort of meant when we see that the surroundings is proportional to negative to delta H because of the added energy coming from an exothermic reaction. The result of that should see our surroundings increase in the amount of disorder. And as we have the endothermic process, removing that heat and energy should allow our surroundings basically to come slow down and be a little bit more ordered. Question on that there. Does the temperature of the surroundings make a difference in whether or not you might see an increase in entropy for the surroundings? So what happens if my surroundings was a super high temperature, right? A really high temperature, and I had an exothermic process that's occurring? Probably that heat and energy that's going to add to my surroundings is not going to make a big difference because the temperature is pretty high to begin with. So that added energy is not going to make a big difference. So for example, if you lit a match just in a room and you could feel the heat coming off the match, clearly do not do this or anything crazy like this as well. But if you took an oven and it was kind of preheated to like 500 degrees or something like that, and you lit a match inside there, off of that match is probably not going to make a big difference in all the heat that's inside the hot oven to begin with. It's not going to make a tremendous difference. So again, don't do anything like that. But the amount of energy coming off into a surrounding that's really high in temperature probably won't have a big effect in an exothermic situation. Obviously, as well, if you had a really low temperature in your surroundings, any energy coming off would make a much bigger effect in that. So with that being said, we can actually calculate the delta S for the surroundings. I'll just rewrite it. It got all messed up there. The delta S of the surroundings here is going to equal minus delta H of your reaction or your system divided by our temperature, and that is in Kelvin. So the temperature does need to be in Kelvin here. Once again, this is the delta S of our surroundings. And I will say this right now, it might not make sense, but if you're calculating the delta S of the surroundings, there is a negative sign. And it's for that relationship that we just talked about. The reason I say that is later on in this chapter, we will rearrange an equation. And when we rearrange the equation, we'll end up with the delta S is equal to delta H over T, no negative sign. So later on, when you kind of rearrange the equation, there is not a negative sign in that rearrangement that we will see. So whenever you're calculating delta S of the surroundings, there should be the negative there. And that's a good way to remember that because people oftentimes put it where it shouldn't be, that kind of negative. So with that being said, we could calculate the delta S of our surroundings using this formula. We could do products minus reactants, calculate the delta S of our system, and we could add both values together. And then we will end up with our delta S of our universe, which again, if it is a positive value, will be a spontaneous type of process. Any questions on that there? All right, so let's try that then. Calculate the delta S of the system, the surroundings, and is this reaction spontaneous at 25 degrees? There's all the values that you would need, perhaps. Give it a go. Okay, so let's take a look. So we're going to try to calculate here, perhaps delta S of the universe equals our delta S of our system plus the delta S of our surroundings. So we'll start with the system here, which again, if they were not provided for you, you would need to go look them up in the table. And again, this is going to be our products minus our reactants. So on the product side there, we have two NH3s, which look like 193. Minus on our reactant side, one nitrogen at 192. And three hydrogens at 131 here. That's going to get us there for our delta S of our system. Our reaction, 2 times 193 minus 192 plus 3 times 131. That's going to give us a negative 199 joules. In this case, remember that this does not necessarily tell us that this reaction is spontaneous, but it does tell us that this reaction is actually increasing the order, right? And decreasing the disorder. We see that by looking at the reaction, we have actually 4 gas molecules, right? And 2 gas molecules. So again, we're have less gas molecules than we started with, so we should expect the delta S for the system or the reaction to be negative. So that does sort of make sense. Now to calculate the delta S of our surroundings, which is equal to minus delta H of our reaction divided by our temperature in Kelvin. So that's going to be a 273 on that. So that's a 298 Kelvin. Here, that will give us negative, and again, there is another negative there from our delta H value, 92.6. I'm going to multiply it by 1,000 to convert it into joules, because frankly, that's in joules, so everything will be the same units, so I don't have any unit issues. I'm going to divide it by 298 here, and that's going to give me 92.6 times 1,000 divided by 298. That'll give me, we'll call it 311 joules. Really joules per Kelvin on both of them, so we're all right. At this point, we can now calculate our universe here. So we got our system, which is negative 199. We got our surroundings, which is positive 311. And in that case here, negative 199 plus a 311. Going to give us basically 112 joules. Is this reaction spontaneous? This reaction is spontaneous. Our delta S of the universe is greater than 0, and it's a positive value. Also, a very good example of not all spontaneous reactions are very fast. This is a very slow reaction if you don't use a catalyst. So this happens very, very slow if you don't add a catalyst to it, but it will happen. So again, when we talk about a reaction being spontaneous, it doesn't really mean that it's going to happen fast or slow. It just means under those conditions, you may have to wait a long time for it to happen, but it should happen, or it may happen really quickly. It just depends sort of on the reaction. Any questions on any of those calculations? Again, this is a situation unit wise. You do want to be careful of the kilojoules and joules, because if you added, 0.311 to your minus 199, you might get a quite different answer. So you do want to watch those units. I personally usually will convert everybody to joules and then convert them back to kilojoules at the end if I need to, but you can't convert joules to kilojoules and do it the other way as well. Typically speaking, like I said before, delta S's are given in joules and delta H's are given in kilojoules. So those are very common sort of ending units, if you will, for each of those sort of values. Any questions on delta S there? Yeah. We're gonna actually talk about some situations a little bit later on where that could happen, and it does have to do with sort of temperature and some other values of what's going on as well. So there are some factors where you can have a exothermic reaction that might not be spontaneous. Yeah. All right. Now, the third law of thermodynamics is the entropy of a perfect crystal is zero and absolute zero temperature. And this is sort of what we've been talking about are if we have only perfect crystal, that would be one way to get that. Gives us a very low entropy of zero. And as we've just been talking about, our phase changes is very common. Increase in entropy as we go that way, a decrease in entropy as you obviously head in the opposite direction. When we have a phase change that occurs, as you may be familiar with, when we look from, say, solid to liquid, or liquid back to solid, there is also a certain amount of heat or energy required just to do that process of taking somebody at their normal melting point or freezing point to go from solid to liquid or liquid to solid. You might remember that is the delta H of fusion, right? Is used to do that. Delta H of fusion, say for water, for example, is like 6.02 kilojoules per mole. That's for water. R, it's roughly like 335 joules per gram, give or take a joule, is the amount of energy required to do just that transition of taking something from solid to liquid or liquid to solid. That, in the case of water, happens at 0 degrees Celsius, so exactly 0 degrees Celsius, which is why you see here a plateau line, flat line. Temperature doesn't change as that transition occurs. It's not until you get above 0 degrees that you really sort of fully transition into liquid, not until below 0 degrees that you sort of fully transition into solid. Right at, say, 0 degrees for water, you got kind of like ice crystals happening, a little bit of both phases occurring. Same thing as you go from that transition of liquid to gas and backwards. There is amount of energy required to do that, which is the delta H of vaporization. And for water, for example, that's approximately 40.6 kilojoules per mole, roughly 2,260 joules per gram. And it's the same amount of energy regardless of which way you're going. The sign just changes. If you're going from liquid to gas, that's an endothermic process, so it will be positive 2260. If you're going from gas back to liquid, that's an exothermic process, so it would be negative 2260. So it's really just a sign that changes as you go through there. By the way, as we change temperature but keep things in the same phase and we want energy, that is our specific heat equation, right? And that's what you use if you kind of keep it in the same phase but change the temperature. But these transitions do occur, and as we'll talk about a little bit later on, there's also what is known as like the entropy of vaporization or the entropy of fusion, which again is the entropy change that occurs as we change a phase of a substance. We'll talk a little bit more about that a little bit later on. So let's talk about another thermodynamic value, and dare I say a different letter, and that is our friend delta G here. So delta G is Gibbs free energy. It is the energy, much like the name implies, available to do some type of work. And as we saw in a spontaneous process, the delta S of the universe will be positive. In an equilibrium process, it will be 0. For Gibbs free energy, we can actually use it to determine whether or not a reaction is going to be spontaneous. And if we calculate Gibbs free energy, or delta G, and the reaction is, and the delta G value is negative, then the reaction is spontaneous as it is written. If we calculate the delta G and it is a positive value, then the reaction as it is written is non-spontaneous. And if you wanted to turn it into a spontaneous reaction, you would need to just reverse it, basically. So you would reverse the reaction and it would be a spontaneous reaction. And delta G is equal to 0 at an equilibrium process. We will see probably 4 different ways maybe that involves an equation that has delta G in it. So there's 4 different sort of delta G formulas, if you will. My recommendation is I would use whichever delta G formula fits the information given to you. That's the best way to kind of choose which one you should maybe use. So for example, here is one delta G formula here, and we could calculate the delta G for a reaction by taking the delta H of the system, which is our enthalpy, minus T, which is our temperature that needs to be in Kelvin, and our S there, which is our entropy that we were just talking about. So this is one of those equations that I was talking about earlier that you use delta H and delta S together. This is unit-wise a situation where you got to be careful. Again, delta H is typically kilojoules and delta S is typically joules. So you do have to do some type of conversion, or you are going to be off by that factor of 1,000 or so if you don't do the conversion. This clearly is the formula that you would use if you're given an H and an S. It seems like the really good formula to use if you're given both of those values. You can plug it in here, make sure everybody's in the correct units. And again, if you get a delta G value that's negative, you'll know the reaction as you're looking at is spontaneous. And if it is spontaneous, what that means is you would expect the reaction to proceed from reactants to products. So you would expect to start making some products in that particular situation. If you calculate it as non-spontaneous, I would actually expect not the reaction to occur in the forward direction. It actually will just kind of hang there on the reactant side, and you should have probably reactants there when you reach equilibrium or just in the end of that reaction. Another very common way to calculate delta G is pretty much just like our delta H and our delta S, which is you can simply take the delta G of your products minus the delta G of your reactants. So just like we do with H and what you do with S, you go to the table, you find the delta Gs. They are also sometimes referred to as standard free energy of formation or free energy of formation, delta GF. And that is really the table values that you find there. Once again, as I mentioned before, the little knot there means standard conditions, and those are pretty much things that are in standard conditions. We will talk about a little bit later on in this chapter what happens when we're not under standard conditions. And again, that means that something's off from that list there. Your pressure might not be 1 atmosphere, your concentration may not be 1 molar, maybe you're not at 25 degrees Celsius. Delta G, much like delta H in terms of units, delta G is typically kilojoules, just like our delta H is typically kilojoules, and our delta S is typically joules. So once again, these are typically the ending units that you typically will have for each of these guys, so you do want to be careful. Delta G is also like delta H in the sense that when you do go to that table, things that are in their standard state, like H2, O2, and those things, they will have values of 0. So kind of like delta H's, they have values of 0. You won't find values here for delta G either. So really it's only delta S that will have values for things in their standard states, like H2, O2, and those type of values. So this would be the delta G that you would want to use if you're frankly just given the equation and you're asked, is this spontaneous, or calculate the delta G, then you would go to the table, do products minus reactants in this case. So why don't we try one here? The values there are on the bottom, and O2 is 0 kilojoules per mole. All right, so calculate the delta G for this guy, and is his reaction spontaneous at 25 degrees Celsius? The table there to find the values, and again, we're going to do pretty much our products minus our reactants here, as we're just pretty much given the equation, and that's it. All right, so on the product side there, we got 12 CO2s, and that looks like a negative 394.4. Our H2O there is minus 237.2, and there's 6 of them, so let's times it by 6. That takes care of all of our products. We'll subtract it from our reactant side. 2 times our C6H6, which is 124.5. And 15 times our 0 there for all of our O2s. And if we do all that good stuff there, 12 times minus 394.4 plus 6 times minus 237.2 minus a 2 times 124.5 looks like a negative 6405 kilojoules in this case. First off, any question on the calculation here? That would mean this reaction, is it spontaneous or non-spontaneous? It is spontaneous, as our delta G here is negative. So our delta G is negative, so it will be a spontaneous reaction in this case. Any questions on that there? So here we would expect this reaction to proceed to the product side in this case. Yeah. So let's take a look at this equation here. Delta G is equal to delta H minus T delta S a little bit more. As I mentioned before, sometimes you're asked questions where, there's like, hey, is it going to be spontaneous, non-spontaneous? Would you expect products or non-products? So you can use a formula like this to answer some of those questions. So for example, if we look at a delta H that is positive, and a delta S that also is positive. Remember as well, unit-wise, kilojoules and joules, which means delta H has like 1,000-fold jump on delta S to begin with. So in this particular case, this reaction will be spontaneous only at high temperatures. And that is because this is positive. The only way to get this part here, which would be negative, the only thing to get it to beat it would be we need a really high temperature here to allow that to occur. So at high temperatures, we would expect this reaction to be spontaneous. At lower temperatures, we would expect this reaction really not to be spontaneous, and would only really proceed spontaneously the way it's written at really high temperatures. Now, if we look at the next sort of situation, which is we'll go with a delta H that's negative, which is exothermic, and a delta S that is positive. That means in this particular situation, no matter what you do at any temperature, this reaction is going to be exothermic, and it will also be negative because this part will be negative basically, and a negative will give you a negative delta G. So this reaction will be spontaneous at any temperature when you have a delta H that's negative and a delta S that is positive. So those are really, to sort of answer your question earlier, Chris, that is sort of the ideal condition for an exothermic reaction to be spontaneous at any temperature is you need also a positive entropy to sort of occur, and you'll hit a spontaneous reaction pretty much at any temperature. So if you have that combination there of those two guys, no matter what you do, you would expect that reaction to be spontaneous. Now, if we had our delta H being positive in an endothermic reaction, and down here, our delta S is going to be negative, because our delta S is negative in this case, it will turn this back part into a positive number, which means no matter what you do at any temperature, if you have an endothermic reaction and also a negative entropy, you will have a non-spontaneous reaction at any temperature, because you're always going to get a positive delta G in this case. So those are the conditions of no matter what you do, you're going to pretty much have that reaction being non-spontaneous. Now, the last sort of combination that you could have here would be another exothermic situation. And in this exothermic situation here, we would have our delta H being negative, which would be down here, and our delta S also being negative. That is going to turn this part of it into a positive number, which means under normal conditions, low temperatures, you will have a spontaneous reaction. So this is one of the places where you can have an exothermic reaction that will be a non-spontaneous reaction if you actually have it at a high temperature. So if you have a really high temperature, that's going to allow the back part of it to really beat the front part, and it'll become a positive delta G. So this is one of the cases where you could have an exothermic reaction being delta H negative, and if your delta S is negative as well, and you hit a really high temperature, it is possible that the reaction would be non-spontaneous as written. So the other factors that sort of affect, obviously are our delta H, and also our entropy has an effect as to whether or not the reaction would be spontaneous. So these are ways that you could use this formula to answer those type of questions. You could also just put numbers in if you wanted to. But these are the sort of conditions that allow reaction either to be spontaneous at any time. And really when that occurs is when we have a delta H is negative and a delta S is positive, you will always have a spontaneous reaction. And a situation where no matter what you do, you will never have a spontaneous reaction. And that's a situation where you have a endothermic delta H, so positive, and also a negative delta S, because that's going to make it positive no matter what the situation is. Any questions on those? All right, so I think actually that's a good place to lay it up. We will stop there for today.